Namaskar, good afternoon, good evening, good morning, depending on wherever you are. It's my pleasure to welcome you all on behalf of the National Data Quality Forum, hosted at the ICMR National Institute of Medical Statistics, New Delhi, to the webinar series organized to discuss and disseminate information on measures being taken to ensure good quality data. My name is Sarita Nair. I'm a scientist with the ICMR National Institute of Medical Statistics and will be moderating today's webinar on Tindering Open Datasets, How Fair are Fair Data? India's emerging digital health ecosystem presents immense opportunities to leverage the data generated for designing timely, appropriate, and impactful solutions for better healthcare for all. However, the ability to effectively harness data for the purpose demands widely available data and quality of the data captured, innovative technological solutions, and demonstrable real-world use cases. The presentation will focus on three major components: technological innovation, curated data sets, real-world decision support use case for COVID-19. So thank you all for joining in. As we start, a couple of housekeeping to ensure a smooth session. All participants except the speakers shall be on mute. We'll be taking chat-based questions. The chat box shall remain live throughout the session. Please feel free to type in your question anytime during the session. Our esteemed speaker discussant will respond to those towards the end of the session. So that's about it. Thank you. Before I invite Dr. Tavpritesh Sethi to deliver his talk, it's my honor to introduce Dr. Sethi. Dr. Tavpritesh Sethi is a physician, scientist, and associate professor of computational biology at the Indraprastha Institute of Information Technology, Delhi, and a fellow of the Wellcome Trust DBT India Alliance at All India Institute of Medical Sciences, New Delhi. He completed his MBBS from Government Medical College, Amritsar, received PhD from CSIR Institute of Genomics and Integrative Biology, New Delhi. Dr. Sethi's research is focused on development and deployment of machine learning-based solutions to enable decisions and policy in pressing healthcare questions such as antimicrobial resistance, maternal and child healthcare, sepsis, health inequalities in intensive care, and public health settings. Dr. Sethi has many publications to his credit and is a recipient of MIT TR35 India Innovators Under 35 Wellcome Trust DBT India Alliance Early Career Award. He's a member of the European Association of Systems Medicine and leads the Australasia region of International Association of Systems and Networks Medicine. Over to you, Dr. Sethi. Kindly unmute.
Thank you, Dr. Nair. Am I audible? All right. So, and please let me know if my screen is visible.
Yes, it is. Thank you.
I'll just move in the slideshow mode. All right. So the topic that I'm going to be discussing today is very close to my heart because we have been working with data for public health almost for 7 years now. Before that, we were working data with data for genomics and allied areas like physiology. But public health is is a place where a lot of data gets generated as a part of government programs, administrative programs, and there's a lot of potential for these data to be leveraged for creating effective interventions. However, there are challenges, as we all know. Data quality is one of those challenges, which I have discussed in one of these previous webinars as well. Today, I'm going to be talking about another challenge, a second challenge, which is tindering or combining or linking data sets to answer questions which can only be answered if we bring these together. So, and the data sets specifically that I will be focusing on are called fair data: findable, accessible, interoperable, and reusable. Why fair data? Because as the name suggests, these are supposedly...
Dr. Sethi?
Yes.
Sorry, we are not able to see the screen.
Let me share it again.
Yeah, please.
Are you able to see my screen?
Not yet. Sorry about the technical glitches. It's yet not there.
Let me try once more.
Yeah.
Yes.
All right. So I was talking about fair data sets. How fair are fair data? Findable, accessible, interoperable, and reusable. Why fair data? Because by definition, these data sets have to
This is still loading.
Okay.
Probably in the presentation mode, there is a problem. Otherwise,
All right. So
I think you can present as it is. It is still loading.
Still loading?
Yeah. So you just don't put it in a presentation mode, just like that we can see.
Okay.
Please reload again. Yeah. Now, can you scroll 1 or 2, sir? Let us check.
Can you see
Yeah,
this?
it is working. I think if it is, I think it is visible. See.
Shall I proceed?
Dr. Sarita, is it visible?
It is visible, although, yes, sir. I mean, I think this is the best possible.
But there is a problem in the presentation mode. Let us see.
Can you see the presentation now, or just put
No,
it?
sir, not yet.
Okay. So
there is some problem.
Says my screen sharing is paused. Hold on. So I'll just go back to the.
Yeah, please.
Because I think that might be the better option. So are the slides moving now?
Yes, it is moving.
Yes, sir.
Now.
Yes, sir. Yes, sir.
I'm sorry about the technical glitch.
Yeah, that's fine.
Browser incompatibility issues.
Please go ahead.
So I'm going to be presenting about the fair data sets, because by definition, these are data sets which are expected to be findable, accessible, but more importantly, interoperable and reusable. So I'll focus on that particular aspect. Along with me, this is primarily the work of a PhD student, Akshaya, who is also here. And she's been working on building these pipelines for helping us basically combine these data sets together. So the goal in this project, or towards this technology building, was essentially learning with heterogeneous data. And the story starts with COVID-19, when we don't have enough data that is available on COVID-19, yet we want to understand what evidence is being generated across the globe. And one source of this evidence is, as research papers get published, many of these research papers are actually, they are required to submit their data to an open platform, especially in COVID-19, so that these can be examined. So we basically resorted to research, peer-reviewed research data as a source of evidence. And I'm going to be talking about making use of these data sets to understand COVID-19 pandemic. So our lab basically solves these gaps that are the data gap, the knowledge gap, and the policy gap. The data gap, as I just said, that there is a lot of data that are available on repositories. However, we don't have the right set of pipelines and tools to make use of these data and also to combine them in an appropriate manner. So basically, we address the problem of data platforms exchange, which is typically a time-consuming process. And from there on, of course, I mean, we can have data, but the proof is in eating the pudding, which essentially means that we have to generate knowledge and also some policy indications that can be gleaned from these data. So our work focuses along these areas, and our lab, many students in the lab work along these lines. So some of the work that I'll be talking about today is available on a portal with linked publications, which have been peer reviewed, and the portal is called Federated Health Platform. .tavlab.iitt.edu.in. This portal actually started way back in 2020 with COVID-19 and is still housing a lot of data on COVID-19 models. Going forward, we are also bringing in more data from other areas such as antimicrobial resistance. Some of the examples during COVID-19 which made use of this heterogeneous data and we were able to make models are also available on the portal. I will give a demo of this slightly later. And these include models such as strain flow, which was one of the, it is a peer-reviewed model, which was one of the first models where we combined, tindered two different data sets, one administrative data, one genomics data, completely different sources, and we were able to make predictive models, which were indicative of the peaks of the pandemic up to 2 months ahead of time in 7 different countries. There's also other models available, such as evidence flow, which works primarily with research publications and that's. But let me quickly go to the main topic of today, which is beyond these, and that is data, because at the background of these is data. So we have about 6,000 COVID-19 data sets. Now also bringing in, and I'll show this live demo as well of the platform. We're also bringing in other data sets, as I said, but these data sets are available as fair data sets with the promise that somebody should be able to interoperate and reuse these data, because that's in the definition of fair: findable, accessible, interoperable, and reusable. So we will see how fair are fair data. And that's today's study that we are going to be basically discussing. And why is this important? Because we believe that unless we have truly fair data, we can have data repositories where data gets deposited. But if these data repositories contain data with fields named like 1, 2, 3, 4, 5, or A, B, C, D, E, or abbreviations, it's unlikely that these data sets can interoperate with other data sets. So we are clearly negating the definition of interoperability. And it's very unlikely that they can actually get reused for any other study as well. So we are addressing this challenge and also then proposing some potential solutions. So where do we find such fair data? There are many repositories available today. Many of these are repositories, for example, by institutions like Harvard. It's called Harvard Dataverse. There are a lot of publicly available open data sets under different licenses. Some may be open, some may be embargoed, some may be open even for commercial use. So there are different levels of licenses in these data sets. But here I'm showing an example from Figshare, which is again a repository which is linked to publications. And here I just searched for the term COVID-19 and data set. And you can see that these examples, 20,262 records come up as of today, which means that there's 20,262 data sets that are available on COVID-19 only on the Figshare repository. Now, all these 20,000 may not be truly data sets, because many times people actually tag them as data sets, but publish them as PDFs, in which case it is not a proper data set. So we actually, in our study, we restrict ourselves to data sets which are structured and tabular. We do not look at unstructured data such as images or unstructured data in the form of let's say videos, etc. So we are only concerned here today with a very simple form of data, which is a tabular data, which is supposedly a neat, clean, organized data. So you can see that these many data sets come up, their sources come up, Figshare, institutions, etc. These also come up. We move forward. Moving forward, these are the platforms examples. For example, this is a data set which says interleukin-1 blocking agents for the treatment of COVID-19, a living systematic review. And you can see that upfront, this poses an opportunity and also a challenge that there can be multiple versions of the same data available. So for example, here's a version data set because it is a living review. So even after peer review, people kept posting the updated version of their findings. Here is an example, version 3 of this data, which is on metabolic perturbation associated with COVID-19, disease severity, and SARS-CoV-2 replication. Again, asking a fundamental question, that is replication of the virus linked to severity, right? A very simple, straightforward question. Many people will be interested in this, especially scientists who are working on omics studies. For example, this is linked with the funder also, a multi-omic systems biology approach to identify disease control mechanisms in HIV positive like controls and importance of HIV. So this is a part of this is the funding that title that supported the study from the Swedish funding. So we get a lot of information about these multitudes of data sets that are posted, because many funders require these days to be posted. So what we are trying to do is not just important for the scientists, but is also important for the funders like ICMR, because a lot of data gets generated. But can somebody use that data to make something worthwhile beyond the study that it was proposed for is an open question. And that's where actually we come in. So this is example tabular data from the same study. You can see COVID-19 healthy control, screenshot of 20 patients, cohorts, interleukin-8, T1 necrosis factor, F9 and TIE2, MCP3, etc. And their levels are being measured. Now, on the face of it, this looks like a clean, well-organized data, right? But this is an example of a good quality data. Now, there are many examples, which are the majority, in which case these field names, they will not be standardized. Somebody will say IL-8, somebody will say interleukin-8, right? So, and if we are going through lakhs of records or tens of thousands of records of such data sets, it is humanly not possible to go into the details of each data. So we are in our lab asked this question, that first of all, to assess that out of all these data sets that are available out there, what is the level of fairness? And then second, can we really propose mechanisms to help harmonize some of these data sets together? And this is an ongoing project. We have published a few papers using this strategy, which I'll be talking about in the end. But more or less, this is an evolving strategy where essentially we are, I'll show some examples of where we stand in terms of improving the harmonization potential of this data. So the problem statement is synthesizing evidence from multiple data sets, which is challenging. And why is this important? Because we also want to build AI models which are more inclusive in nature. So for example, if we want to have questions like how good is a marker, for example, ferritin, for mortality in COVID-19 in Indian patients. Now that may not be addressed, but it may have been addressed, for example, for African patients, or maybe for the Caucasian ethnicity. So that is only possible if we can actually combine these 4 or 5 different sources of data and come to evidence synthesis. Typically, evidence synthesis happens at the meta-analysis level, and we look at the published findings and we basically see some of these, but we are stepping one step behind and trying to understand the data. Because we can, for example, include some of the ethnicity or gender or age variables as covariates in AI models, so that we can actually build unbiased models. So it is important to curate more and more data sets to build models that generalize across data sets. And so that was the motivation behind the study, to create a robust framework. And some parts of it are purely engineering. For example, mining these data sets, right? Creating a data lake from these data sets on an ongoing basis. Every week, there's some data that gets submitted. We can actually put in the algorithms which can, for example, scrape the data from Figshare and Zenodo and put them in a repository which is being continuously updated. So that's what we do in our lab on an ongoing basis, specifically for the data sets that are open data sets and the licenses are permissible, right? So permissive licenses are something that we can use easily. So basically, we download these data sets on an ongoing basis, and then we also download the metadata for these data. So as I was showing earlier, this metadata description is available many times for these data sets. People will actually submit, scientists will submit their descriptions of the data, which is typically not considered as a part of the data, but we believe that that has a strong information about the data as well. And then we use the metadata to build models that are AI models to understand how similar are data in the metadata space. So essentially what we have proposed here is a 5-layer mapping strategy, which we call the Tindering datasets technology. Essentially, if I want to take 2 or 3 datasets together, they should have some checks of how many layers are they actually able to map on. So are they mapping on similarity in the description space? Are they mapping on similarity in the field space? Are they mapping in similarity in the data distribution space? And 2 aspects that we have not addressed as of now is, are they matching in similarity in the model space? Because when we have these data sets, we can actually compute the structural Hamming distance between the models that are generative models for these data sets and say, are the underlying models generating these data sets similar? Right? So I'll be only talking about 2 layers today, because that's where we have been able to go so far. But the next 2 layers are also underway. Okay, so the layer about the AI-based description level and the layer about the field level mapping, which are huge exercises by themselves too. So Beautiful Soup and Selenium libraries were used to basically collect data from these repositories on an ongoing basis. Figshare is an online digital repository that provides a platform to store, share, and discover various data. Zenodo is also an open repository, which is a European repository, which is operated by the CERN. So, and there's many other, there's Mendeley, there's Harvard Dataverse, but these 2 we found that were quite representative of open data. And so you can see there were about 1,640 files that we worked with, and then there were CSV files, there were XLSX files, there were XLS files. You can see about 300 CSV files and about 1,339 XLS and XLSX files. We restricted ourselves to these because these were the these were the most common data files available, but our pipeline is extendable. So for example, there are other files like .sav files, which are SP or .spss files, data files and SPSS. We can easily work with them as well. The challenge being that then we have to really work with the transformation layer, which basically converts those files into CSVs files. That's not too difficult, but we restricted ourselves to the, so this is our inclusion and exclusion sort of criteria. So the level 1 is descriptions. So let me just quickly give a live example of this so that it becomes more relatable. So can you, so can somebody tell that they can see the portal?
Yes. Yes.
So I'll just go to community data. This is a live portal. And this is, as I said, collection of approximately 6,000 pre-processed data related to COVID-19, and give some description of the plots that you're going to see shortly. And it basically has some things, some embeddings that have been generated using BioBERT models, which are transformer-based AI. And I'll give a background to that. But you can also see that you can actually explore these data sets. For example, Zenodo, Finland, basic reproduction number of a virus, right? And then you can get top similar files, but this is something which we'll do later. But if I click here, it will take us to an embedding projector, which will load the model, which I'll talk about shortly, in the similarity space. So here is a t-SNE model. Right? So you can see that each of these dots here is a data set. So each point here is actually not a sample, but it is a data set. Now let me pause it. And if I had run this slightly more, you'll see more structure emerging in this. Actually, let me resume it so that there may be some more structure to help us visualize the data sets. Yeah, I think this is fine. So I'll pause it again. And now if I actually, let me maneuver this around. If I click on these 2 points, which are very close in time. So this is, I click here. This is a data set which is quite outside of the general cloud, right? This is a molecular dynamics trajectory of the SARS-CoV-2 spike protein. And then there was another similar data set, which was similar, that basically this is a biochemistry. We use at UCSD, we use biophysics and high performance biocompute to fight COVID-19. Now you can see this example where some biomolecular data sets have come together in the description space, these two data points, right? And these two data sets, why have these come together? Each point, remember, each point here is a data set. Actually, each point here is a description of a data set. And what we are using here is something called a transformer model to create a low-dimensional embedding of dataset descriptions. These are text models. I'll switch back to the presentation. To just give a brief background of what these models are, right? So everybody has now heard about ChatGPT, which is an example of a text model, which can understand language and give responses. Similarly, this model is also based on the T in GPT stands for transform, general purpose, general pre-trained transformers, right? So transformer model is basically proving to be one of the most successful models in understanding language. It can be used to understand literature. It can be used to understand social media. It can be used to understand even, for example, these descriptions of data sets to help us ask which data set should I choose for mapping to this particular data set in a very ChatGPT-like manner, right? And remember, this was before ChatGPT. This project started before ChatGPT was announced and an example started coming in November. This was basically, we were running this project since about 2021, early January. So 2022, early January, sorry. So the transformer model basically uses something called attention models, which is simply that these AI models learn to pay attention to each word in the sequence, and then they try to understand the language. And since these models have been fed with millions or billions of documents, they can learn patterns from language which are contextual. For example, if I'm asking a question, how is your sister? How does the model know thank you? And the next word has to be she and not he. So the model has to somehow learn that the context is sister, it is not brother, it's a female gender. So that kind of modeling happens in these transformer-based approaches, which obviously we don't have the time to go into today. But that is in short is called the attention mechanism. That to give a prediction about every word, the model has to attend to the context of the previous sentence or the sentence. So basically it pays attention to the entire sentence. And then billions of sentences are used to create this context vector. And using these context vectors, neural networks are trained, and those neural networks basically are then able to, quote unquote, understand language. Here is an example of making, trying to convince you that it actually works. And this is not our example. This is a transformer, openly available transformer example, where it says the animal didn't cross the street because it was too tired. Right? The attention mechanism tells that, this is called self-attention, that the word it is pointing to animal. If I change one word in this whole sentence, which is on the right-hand side, the animal didn't cross the street because it was too wide. Now you can see the heaviest attention is coming from street. The street was wide. And this is an example where the model learns to pay attention to context and to understand what is this it referring to. Is it referring to the animal or is it referring to the street? So this is the exact kind of model in BERT that we used in our transformer layer 1 to create the Tindering dataset layer 1 of dataset similarity. And it is based on a BERT model, specifically a BioBERT. BioBERT is a pre-trained biomedical language representation model for biomedical text mining. It is openly available. But what we did new was we actually used the cosine similarity of these datasets. I'll share the details of the BioBERT paper shortly. But what we used was, remember those two data points coming together, though they are together because in the vector space, in the underlying vector space, in the vector space model, they have a high cosine similarity. Cosine similarity is nothing but the dot product of two vectors. If the dot product, if the angle is 0, cos is highest, 1, cosine similarity is highest. If they are orthogonal, the cosine similarity is low. And that is one way where you can actually map the language to vector spaces, and then we can do algebra with the vector spaces, which basically tells us that we can ask questions like, give me a data set which has COVID-19 and immunology, but it does not have interferon gamma. So this is vector algebra, so which is just adding and subtracting vectors to point to the right data sets. That is the first layer that we basically do for description level similarity. So we had about 2,219 descriptions, as we said in the CSV files, with which we trained the BioBERT model. So because BioBERT is not trained on this particular, we had to retrain it on this. We took the pre-trained embedding and we generated new embeddings, calculated the cosine similarities, and we look at the distribution of this. Right? And since this is all COVID-19 data, this distribution actually helps us to set thresholds that we don't want to go below, for example, 0.6 of cosine similarity when we are looking at data similarity in the description space. We do see multimodal distributions. That's something that we do find, and we believe that that's because of the clustering of data sets, for example, in social media space and molecular space and administrative data. But more details need to be done there. The next layer basically talks about, once we know that two data sets are coming together, we still cannot actually work with these data sets unless we have the same fields in the data sets. One person may have entered IL-8-6, another person may have entered IL-6. So these have to be interoperated, right? And that interoperability is the major missing piece in most of these data sets. So what we decided is to actually map as much as possible these terms to the SNOMED-CT ontologies. And SNOMED-CT is Again, I don't have the time to go into that, but it is a framework that is basically used. It's an ontology. It is a resource that basically is a directed acyclic graph, an ontology, which has parent-child relationships at very high levels of detail and is a very well accepted approach to harmonize data sets. So coronary heart disease, coronary artery disease, these will fall under the similar category in a concept, and it will have synonyms and fully specified names, and then it will also have relationships, and it will have a structure to that. So we decided that we will map these fields. Once we know that these data sets come together, we will look at their field names and then try to harmonize these back to the SNOMED city. We thought that it will be difficult, but we didn't realize how difficult it is, right? There were about 1 lakh columns because there were multiple versions. So we only had about 1640 unique files out of these with 1 lakh columns. And mapping these 1 lakh columns to SNOMED city terms. And then we also said that we'll choose a Markov blanket. It may not be an exact SNOMED city term. It may be something within the Markov blanket, which is parent, children, and siblings of that term in the net. So we basically map that because we want to understand that what is this IL8 referring to, which a computer should understand and then should be able to reason. So we basically establish a common language for different data elements present in the data, right? But to our surprise, only 218 out of more than 1 lakh, whatever number was there, had an exact match in SNOMED city. And that is our first level. I mean, we talk about data quality from many different aspects, but here is another challenge in fair data, that only 218 field names mapped in 1:1 exact mapping to SNOMED city terms. And in our paper, actually, we have not published that paper yet, but it's under preparation. But this is one of the key points, that how fair are fair data? Can we really work with data sets where interoperability is so low that only less than 0.1%, 0.01% actually are mapping to a standard terminology like SNOMED city? And these are all biomedical data sets. So one recommendation that we do is that, just like genomics, where we had a minimal information about a microarray data set or minimal information about a proteomics data set, we should have some minimal criteria, mappings of terms that we should keep. And these may be ICD, SNOMED city, but typically there should be some level of interoperability. There were about 15,000 terms which were mapped, but these were mapped to multiple, which means that these have to be disambiguated. We don't really truly know what is the exact meaning of that term. Maybe diabetes mellitus, it may be diabetes insipidus, and so on. And there's a lot of terms which have no maps, 0 maps. And those are typically columns where people have actually put in 1, 2, 3, 4, 5 as column names. And, or even A, B, C, D, E, or dates as column names, which is possible. We are not contesting that. But 1, 2, 3, 4, 5 is definitely not an interoperable data set. Dates, perhaps yes, because many data sets contain the epidemiological data that how was the COVID-19 evolving. So that is one of the major finding, that 85,873 columns remain unmapped and were irrelevant for our analysis. And some of the 1:1 map fields are, for example, things that we expect. And these are examples from the 1:1 map. We next proceeded to our layer 2, that we will disambiguate, try to disambiguate, because we thought that there may be data quality issues, there may be exact matches, or there may be some matches where there may be some confusion. So we used things like spelling correction and disambiguation. Disambiguation, we used again the Markov blanket concept, and we refine whatever is possible with some margin of error. And I think I would give this disclaimer up front, that on our portal, we actually leave it to the researcher to choose what threshold of cosine similarity do you want to work with, or what threshold of Jacquard similarity do you want to work with? Because we don't have any recommendations unless we do a million data sets to say that this is the threshold that we should choose for this kind of data. But what we currently leave is basically we say that if you want disambiguate, we give you thresholds to work with on the portal. But in our COVID data set, we were able to use this basically to find more exact matches. Typically about 6,014 were now mapping exactly, which is a good number because from 200 to 6,000, we are after disambiguation and spelling correction, we are able to do an exact match. Still, major proportion is unmapped. Right? So we were able to push back the boundary of mapping here again. And here are some examples again, which, I mean, there may be some examples where somebody has spelled sex incorrectly, right? Or age incorrectly, gender, date, activity. I don't know what PI exactly stands for, but PA view is, for example, in X-rays and so on. Here are some more examples, right? So, and one thing I would like to mention here is that we not just disambiguated, but we mapped them to the preferred SNOMED CT term. Because one of the downstream tasks is, remember, tindering datasets, that we want datasets to have common field names so that we can actually combine at least subsets of these datasets together and build integrated models. So that is the, and the way we do that is basically, we look at in a dataset, if there were 1,000 or 100 fields, what is the Jacquard similarity? And there was another data set which had maybe 200 fields. What is the Jacquard similarity? Which is just intersection over union of preferred SNOMED CT terms. So essentially, which tells us that how much is the overlap of field level similarity between these data sets. And we give it as a tunable parameter portal. So what have we covered so far? We have covered how similar are data sets in the description space, and then we go to Jacquard similarity space. How similar are the data in the Jacquard similarity space?
May I request Dr. Tam to wind up in 5 minutes?
Okay, I'll skip some of these. Sure. And this is the intersection over union, Jacquard similarity. We do some normalizations, right? But to cut a long story short, this is available on the portal. I'll just very quickly mention some use cases. Use cases that we are able to run with these kind of things is to run an integrative model for pandemic preparedness, which combines data on strains, mobility, and data sets that are, for example, health and social and economic data sets. And this paper is under review in EMEA currently, and we are coming up with a next follow-up paper where we used latent space models to actually tinder or combine these data sets together in the integration. So we do have some proof of concept analysis and studies put out where we show that how this approach works to find the relevant data sets and then to be able to combine them. What we need to do is to put confidence levels on each of these, and that, as I said, will require further a large number of million maybe data sets to come to what thresholds should be set with what confidence. But already we see, for example, for our other published papers, for example, genomic surveillance models, this has worked, where we combine data sets on genomics and administrative data together. I know I'm running out of time. It is available on the portal, the use cases. So the conclusion is that evidence synthesis in the data world, previously evidence synthesis was mostly in the meta-analysis space. In the data-driven and AI-driven world, will bring more and more data together for creating and synthesizing evidence. Fair data sets are not fair. We really need to work on even research-grade data sets. We'll come up with some recommendations in this paper. We show some of these examples that how low is the number of 1:1 exact mapping, or even after disambiguation, it is hardly 1% of the terms that get mapped, even after doing state-of-the-art AI approaches. And so that is the challenge that we currently face with open datasets. We do believe that even with this level, we are able to find datasets and tinder them together, combine them together to answer those questions. But there's a lot to be desired, and the study basically is just a starting point. Some of these papers are peer-reviewed and openly available. As I said, some are currently under review and some are under development in layer 3 and 4, for example, the structural Hamming distance. I probably will be talking about in one of the next presentations, which is based upon something called the model similarity, which we have done some experiments with as well for the data sets. But I'll stop here and questions. Thank you very much.
Yeah, thank you. Thank you so much, Dr. Tavpritesh, for the detailed presentation and in fact, the brief live demonstration also. So before we invite our distinguished discussant, I have the honor of introducing Dr. M. Vishnuvardhan Rao. Dr. Rao was the former director of ICMR NIMS, and under Dr. Rao's able stewardship, the National Data Quality Forum was initiated in 2019. Dr. Rao has nearly 3 decades of research experience in health and nutrition with specialty in biostatistics, big data, and information technology. Dr. Rao has published more than 150 papers in national and international journals. And Dr. Rao is a recipient of several awards, including the NAMS Oration Awards for the year 2019, Fellow of Indian Society for Medical Statistics in 2022, Fellow of Telangana Academy of Sciences in 2023. I invite Dr. Rao to kindly express his perspective. Thank you, sir.
So thank you very much. Am I audible, Dr. Sarita?
Yes, sir. Yes, sir.
Yeah. Thank you. It is my pleasure actually when being in this group, because one of our good friend, Dr. Tavpritesh, and actually I like him because he being a doctor and also a very great computational scientist. And also Dr. Sarita Nair, who is one of our good scientists of National Institute of Medical Statistics. And I'm very pleased to be there with them. So I just start with good data beats the opinion. So if you have the good data, it will beat the opinion, whatever you have. So I also refer this that Clive Humvee, a British mathematician, coined the phrase, data is the new oil. And you all know that the oil-rich Gulf nations transformed from camel to Cadillac car, just as crude oil is transformed into more useful products. Similarly, the raw data needs to be pre-processed and before it can be used for final analysis. So I really like the title of the topic, how fairer is the fair data. So Dr. Tao has very elaborately given the procedure, though it appears to be very simple graphics, but it has got a lot of computational. You need to have a lot of computational ability and need to understand the some of the mathematical statistics behind that. So as you are harping on the fair data, the findability, accessibility, interoperability is very important, and reusability, that is the one which all the open sources are meant for. So therefore, while using the what you call the open source data, it is easy to find many open source data, but you have to really look into the duplicate data in that, and inaccurate data definitely will creep into that, and ambiguous data as well as hidden data. Hidden data means they give only part of the data and remaining they don't share, or they don't give in the open source, and inconsistent data as well as too much of data. So data magnitude, suppose in statistics we say that if you always the big is not beautiful. If you increase the data, the type 1 error will increase. Therefore, finally, our endeavor would be guide to use appropriate methodology of data in a manner to produce, validate, interoperable, and reproducible results. That's what Tao has very clearly mentioned. But before I go to the questions, I would like to ask Dr. Taoji whether suppose a person, because everyone is not a very good computational expert or a statistician, suppose they want to use the open source databases for their regular research or for their research point which they want to prove. how difficult it is, or what are the simple what you call techniques or simple ideas you can give to them whenever they want to use the open source data without compromising the quality of the data. That's what I would like to ask Dr. Thawapathy Setiji.
Thank you,
Thank
sir,
you.
for that question. I am actually slightly biased towards the use of data. So I definitely see in the last, our experience with this actually started in 2013. And the findings of that study was published in Lancet Global Health, where we were able to combine data which was coming from a single day point prevalence study done by Chest Research Foundation, Pune. So single day, 2 lakh patients collected all across India on symptoms which are ICD mapped. And when this data came to us, I was analyzing that data. So one of the first examples was basically I put the data, I wanted to ask, if I put this data in the context of districts where this person is coming from, because we had the district level information, and I take some indicators of the district, do I get some additional information? And I was naive in asking that because I really did not have a lot of insight into how dirty the data might be or whatever the quality may be. But even with that, basically, since it was a large, at that point of time, 2 lakh was a large number. 2 lakh patients was a large number. We basically constructed a Bayesian network model. And with the hypothesis that if there was noise and random noise, then basically we will not find associations or causal. But what we did end up finding was there was a very clear data-driven directed association, parent-child association from LPG consumption across districts and level of COPD in the patients. COPD is chronic obstructive pulmonary disease. And the inference of the Bayesian network actually showed that if we increase the level of LPG penetration into districts, the level of COPD will decrease in the districts. And that was basically a very clear indicator why we need clean cooking fuel, because one of the main causes of non-smoking COPD is unclean chula burning and firewood burning. So that generated some evidence, and that was one of my first. So since then, basically, we have tried numerous number of times doing such exercises where we do put context to our public health data by looking at openly available data. It is not always easy. They need to be clean. Many times they need to be harmonized. For example, even during this COVID-19 exercise, we are working on a project where 3 different sources will have different district names. I mean, district names from vaccination counts will be different from, let's say, another source of data for tests will be different, and district names coming from Twitter will be different, and so on. So there has to be a lot of work that goes into harmonizing these data sets, and that's still a major pain point in all of this. Yeah. But yet I believe that if we have to build models that give us policy insights, we have to really put these models in context, in local context. So that's why these are important. I think it's not very difficult to find these data. Findable is not a problem. These repositories have a lot of data. Harmonization is a major issue. That's what we talked about. And then basically a lot of, even after we do this, we do a lot of exercise in, does this even make sense? Bootstrapping and all of this to understand really are the models reliable and so on. So I think that requires some level of statistical expertise. But finding and putting together data, maybe and starting working with it, building simple models is not so difficult.
Thank you. I think many people will be contacting you for this. Definitely, they must be interested to know how to get fair data from the open sources. That is very important now, because 2.5 quintillions of data has been generated every day. So enormous data is available. So how to best use of that data is very important. I think you have given a lot of examples for that. So I would like to take 1 or 2 questions from the. Yeah, Dr. Ashish Fakre, he's asking, any suggestions for data on mental disorders on similar platform? Could you please show any example of studies conducted on mental illness using these methods?
We did publish a paper from surveys conducted in the US on learning the impact of COVID-19 on mental health. And those surveys I mean, those were in a structured format. But we did make use of open data to basically show that what were the indicators or what were the predictors of mental things like anxiety. So, for example, we find in that even talking to a neighbor is more effective than picking up the phone and talking to your relatives, right? I mean, it's controversial because then we have to be masked up and maintaining distance. But those are some findings that is available, and the title of the paper is "Learning the Mental Health Impact of COVID-19 in the United States." That's a paper published from our work. It did not involve any tindering, but it involved open data sets and building Bayesian network models and finding the impact. There may be many other papers along similar lines because mental health has been widely studied. So that's a great point. If you want to study that, you can apply that. What we are doing right now is we are taking this out of COVID and also applying it to other diseases. So if you want to do a case study on mental health, we would love to. I mean, you can take our pipelines and apply, and we'll love to collaborate. And if you're an expert, yeah.
That's good. So one more small question by Dr. Tirupati Reddy. He says that he's asking, we have a structured data, how it can be, he has unstructured data, how it can be converted into structured data, what methodology can be used, and how it can be validated.
So it's a big area of advancement now. Unstructured data, especially text data, can actually be used to convert into structured data, and we have used those as examples in our models. I'll give one short example. If we have text, text is not numbers. How do we convert text into numeric is something called vector space model. I briefly touched upon it, that each word, for example, the king, the word king can be embedded in an underlying mathematical space called the vector space, where king is a vector. It has a certain direction and a distance from the origin. And then basically we expect that king and queen vectors are going to be close together. And king and woman vector will be closer together, and king and man vector will be closer together. So the first example where this kind of analysis happened was called the word-to-vec model by Google, where they showed that they could do word algebra using language, saying king minus man plus woman is what? And it'll tell you queen. So because you could actually convert unstructured data to underlying structured numeric quantities, values, which are called vectors in the underlying space. So that is one example where for each word you will get a table that in dimension 1, the vector weight is X, the dimension 2 vector space is Y, and so on, blah, blah, blah. And essentially then basically you can use it. Other data sets like video data sets are also being treated similarly by using the latent space models, where basically diffusion models is one example. DAL-E is an example where generation of images is happening by using video data, learning the underlying vector space, and then basically learning how to create sample from the underlying vector space, which is very similar, by the way, to PCA-like approach, which is used in standard statistics, but now in a much more data-driven manner and neural language. So.
Nice, thank you. So last question, if at all any questions left out, and we'll post it to you, sir, and you can answer them, and we'll communicate to them. And Kanika Sandal is inquiring about how AI can be used to improve disease surveillance and early detection system, and also how big data can be used to address the unique needs of different populations, especially for public health.
We are huge. I mean, we are very, I would say, gung-ho about the use of AI in both of these. Our lab has been working in pandemic preparedness. We used AI to understand the genomic sequences and say, how is the virus evolving? And that's where our the strain flow model was actually able to show 2 months ahead of time, 7 different countries, that a new strain is coming, which may lead to rise in cases. And that was working across all 3 waves in India. We showed that conclusively, and more follow-up papers along those lines are also coming up. So we do believe that AI has a strong role to play. If you look at not just, for example, genomic data, but even social media data, we asked in another paper, which is not published yet, it is under review, where we say that ask what are the carriers of misinformation on social media. AI used to understand what are the emotion carriers of misinformation. Is it anger? Is it trust? Is it joy, sadness? So what kind of emotions are being used to transmit misinformation in different geographies? Again, AI has a huge role there, because without AI, we cannot understand language and we cannot understand the emotion that is linked to that language. So you can understand, because with misinformation would come a lot of spread. Those are just two examples from our own lab, but I believe there's plenty of examples where you can use these different signals, social media, mobility,
absolutely,
and so on. Yeah.
Yeah. So one more one sentence question, like Anupam Kumar Das is inquiring, how can we make our data sets to linked data?
Linked?
That's what, yeah, linked data.
Linked data. So I think we have to find some dimension which is common. And the strategy that we use is basically we learn the latent space of models, as we were saying, using the unsupervised modeling approaches. But we do have to have as many as possible, at least a few. For example, what we typically do is we look at geography and time, spatio-temporal, right? We say spatio-temporal context. So spatio-temporal, without actually identifying which person, we can actually use spatio-temporal and maybe ethnic dimensions as three gluing dimensions, in which then we can glue the vector space of these data sets, the underlying vector space. So I think that's where linkage can happen without identifiability of a person, which is privacy constrained and so on. So that's exactly what we do. That's just one.
Thank you very much. It was a fantastic evening and we had a very good talk, and definitely this will go a long way, and we have to actually understand the actual ideas of this, but some few people only are doing this, and it is very much needed right now. And of course, the Honorable Prime Minister's Digital India Initiative, this would become a great help if at all we work on this in coming 10 years. India will be the data-rich country. And thank you, Dr. Setiji, and it was nice interacting with you, and excellent presentation. Over to Dr. Sarita.
Thank you so much. Yeah, thank you so much, Dr. Pritesh, for making an interesting presentation. And thank you so much, Dr. Vishnu, for making the discussion quite lively. And of course, a big thank you to the audience who have been, there up till now with us, and then have been asking questions. So if there are more questions which are still unanswered, please write to us. We will get back to both the panelists and then get back to you. So thank you so much. We close this session. Thank you.
Thank you very much. Thank you very much. Nice meeting all the old friends.
Thank you so much, sir. Thank you.